Swayam Prabha. Digital India. Educated India.
Photochemistry Module 6 Lecture 2. This is Mallika Pathak from Miranda House, University of Delhi. The academic expert of the course is Dr. Amrita T. Sheikh, and the recording is being done under the DTH Swayam Prabha project of the MHRD, New Delhi. Now, in the previous class, we started with the topic of photochemistry and we looked at the laws which govern photochemistry, followed by a derivation and the in-depth analysis of Lambert's law and the Lambert-Beer's law. Then we also looked at quantum yield and how a quantum yield is calculated. And what are the reasons of low and high quantum yield. Now today, continuing with the topic of photochemistry, we will be looking at the various methods used for the determination of number of photons. The methods that we will be studying is the use of thermopile or a chemical actinometer. Then we will take a look at what are the various kinds of luminescence through the use of a Jablonski diagram, followed by what is photosensitization. The quantum yield of any photochemical reaction is measured using an experimental setup which is shown below. Now this experimental setup was also shown in the previous presentation, but let's take a relook at it. So we have a light source here which emits radiation of suitable intensity in the desired spectral range. The commonly used sources are filament lamps, carbon metal arcs and the various gas discharge tubes. It also has a lens of suitable focal length. Then there is a monochromator or a filter which cuts off all radiation except the radiations of desired wavelength. Then there is a sample keeper or a cuvette. This cuvette can be made up of glass or quartz depending upon what kind of radiations are using. Glass is used for visible radiations and quartz is used for UV radiations. Then we have a detector which could be a thermopile or an actinometer, and we want to study about the thermopile or the actinometer which are used to measure the intensity of light radiation. So let's take a look at both of them individually. So the amount of photons that are absorbed are counted either with a thermopile or a chemical actinometer. So what is a thermopile? A thermopile is made up of large number of junctions of two dissimilar metals. One set of junctions of the thermocouple is blackened so that it can absorb all the radiation and is maintained at constant temperature by placing it in a box. The radiations that fall on it are almost completely absorbed by it. As a result, this set of junctions becomes hot. The temperature difference between the hot and the cold end produces a thermoelectric current, which is measured by connecting a milliammeter to the thermocouple. By calibrating the thermopile with the radiations of known intensity, the intensity of the desired radiations can be measured. And we have studied about these thermocouples when we were in 12th through the thermal effects of electric current. Now, thermopile are nothing but they are sensors. A sensor which is made up of two dissimilar metals. And we know that when you put two dissimilar metals in contact with each other, then across the ends some temperature difference is generated, and which leads to the production of electric current. So moving to the chemical actinometer. So what is a chemical actinometer? A chemical actinometer is a device in which gas mixture or solutions sensitive to light are used. It is dependent on the use of photochemical reactions of known quantum yield. The working of this device is based on the fact that a definite amount of radiation brings definite amount of chemical reaction. So the most common reaction which is used in the actinometer is the decomposition of oxalic acids sensitized by uranyl ion. The uranyl ion is UO2 2+. This absorbs radiation in the wavelength region from 250 nanometer to 440 nanometer. The excited uranyl ion transfers this absorbed energy to the oxalic acid, which then gets decomposed. So uranyl ion will absorb energy in the region of 250 to 440 nanometer and will get excited. This excited uranyl ion will then transfer its energy to the oxalic acid. This process is called as sensitization. Now oxalic acid will then get decomposed because it has become excited by the receiving energy from uranyl ion, and gets decomposed to give you carbon dioxide, carbon monoxide and water, and the uranyl ion has gone from the excited state to the ground state. So in this case, if you know the initial concentration of the oxalic acid and you also know the concentration of oxalic acid after the decomposition has taken place, you will know how much of the oxalic acid has decomposed. So this is done through your titration of oxalic acid with KMnO4. The quantum efficiency of this reaction is 0.57. So if you know the amount of oxalic acid that is decomposed, you will also know the amount of photons that have been absorbed by the system. So to understand this better, let's take at this numerical, which will give us a better understanding of how a chemical actinometer works. So in this reaction, 10 centimeter cube of a solution of 0.0495 mole per decimeter cube of oxalic acid and 0.01 mole per decimeter cube of uranyl sulfate was passed a radiation of 254 nanometer. After the mixture had absorbed 88.1 joules, what is it? 88.1 joules is the total energy that has been absorbed. The concentration of the oxalic acid was found to be 0.038 moles per decimeter cube. So initially the concentration of oxalic acid was 0.0495 and finally it is 0.038 mole per decimeter cube. How have we determined this? By titration with the KMnO4. Now what is the quantum yield at this wavelength for the decomposition of oxalic acid? What is it that we want to calculate? We want to calculate the value of the quantum yield for the decomposition of oxalic acid. Let's try and do it. Now what is the first thing that we do when we look at a photochemical reaction? We find out the energy corresponding to a particular wavelength. Here the wavelength that is used is 254 nanometers. So we will find out the energy corresponding to it. So we use the formula NaHC by lambda. We substitute the values of Na, H and C and lambda in meters. You get the energy is 4.714 into 10 to the power 5 joules per mole. So 1 mole of photons of wavelength 254 nanometer corresponds to this energy, 4.714 into 10 to the power 5 joules. Now we know that the total number of energy that was absorbed was 88.1 joules, and you can also take a look at the units. So this is joules and this is joules per mole. So if you divide joules by joules per mole, you will get the number of photons that have been absorbed. So you divide 88.1 joules by 4.714 into 10 to the power 5 joules per mole, and you get the number of moles of photons that have been absorbed by the system. Now we know that quantum yield is equal to the amount of molecules reacted upon amount of photons consumed. So let's find out the amount of molecule reacted. So here in this case we are talking about oxalic acid. So amount of oxalic acid reacted in 10 centimeter cubes of the solution is equal to, we were given the initial concentration was 0.0495 moles per decimeter cube, then the final was 0.0383 mole per decimeter cube, and we were given the volume as 10 centimeter cube. So we convert appropriately mole per decimeter cube into mole per centimeter cube and then find out the value for 10 centimeter cube. So we get the number of moles is equal to 1.12 into 10 to the power minus 4 moles. Therefore now we can calculate the value of quantum yield. What is quantum yield? Quantum yield is equal to amount of oxalic acid that has reacted upon amount of photons consumed. We know the amount of oxalic acid that has reacted, we know the amount of photons that have been absorbed, and we can get the value of quantum yield. So the quantum yield is 0.599. Let's take a look at another example that is there. The absorption of UV radiation decomposes acetone according to this reaction. So you have acetone which absorbs light and gets decomposed to give you ethane and CO. Ethane and CO. The quantum yield of the reaction is 0.2 at 280 nanometer. A sample of acetone absorbs monochromatic radiations at 280 nanometer at the rate of 7.5 into 10 to the power minus 3 joules per second. Calculate the rate of formation of carbon monoxide. So let's find out what is the first thing that we do. We are very familiar with it now. So we find out the energy corresponding to 1 moles of photons for this wavelength 280 nanometers. So we use the formula NaHC by lambda, substitute the value of Na, H and C, 6.022 into 10 to the power 23 per mole for Na, 6.2626 into 10 to the power minus 34 joules per second for Planck's constant, and C 3 into 10 to the power 8 meter per second for C, and then divided by wavelength in meters. We get the energy corresponding to 1 mole of photons, and the units will be joules per mole. Now we know that the total energy absorbed is 7.5 into 10 to the power minus 3 joules per second. So we can get the energy of photons or the amount of photons absorbed per second by dividing this with this. So we get the moles absorbed per second. Now we know that 1 mole of acetone was decomposing to give you 1 mole of carbon monoxide. So we can find out the amount of carbon monoxide produced in 1 second. So we have amount of photons absorbed, we know the quantum yield, and we just multiply the two and we get the number of moles of carbon monoxide produced in 1 second. Let's look at the consequences of light absorption. Now, according to the Grotthus-Draper law of photochemistry, only that light which is absorbed by a system can bring about a chemical change. However, it is not essential that the light which is absorbed must bring about a photochemical change. The absorption of light may result in a number of other phenomena as well. For example, the light absorbed may cause only a decrease in the intensity of the incident radiation and is governed by Lambert-Beer law. The light absorbed may be re-emitted almost instantaneously, and this phenomena is known as fluorescence. This fluorescence ceases with the removal of source of light. Sometimes the light absorbed is given out slowly and even long after the removal of source of light. This phenomena is known as phosphorescence. The phenomena of fluorescence and the phosphorescence are best explained with the help of Jablonski diagram. In order to understand this diagram, it is necessary to define some terminology. Most molecules have an even number of electrons. Thus, in the ground state, all the electrons are spin paired. The quantity 2s plus 1, where s is the total spin, is known as spin multiplicity of a state. When the spins are paired, as shown in the figure, the upward orientation of the spin is cancelled by the downward orientation, so that s is equal to 0. How does it come out to be? S is equal to S1 plus S2. S1 here is plus 1 by 2 and S2 is equal to minus 1 by 2. So S is equal to 0. Therefore, the spin multiplicity 2s plus 1 will work out to be 2 into 0 plus 1, that is equal to 1. And the spin multiplicity of the molecule in this state is 1. This is called as the singlet ground state and is represented as S0. Similarly, what can happen is this molecule may absorb a suitable quantum of energy, and one of the electrons goes to a higher excited state. The spin orientation of the two single electron may be either parallel as shown here, or they may be anti-parallel as shown here. Then in that case, again we can find out the value of spin multiplicity. If it is anti-parallel, then obviously the total value of S will be again equal to plus 1 by 2, minus 1 by 2. So this will come out to be 0. So 2S plus 1 will be equal to 1. Therefore, it will be a singlet state. But because it has been excited to a higher energy level, this is called as a singlet excited state. But if they are parallel to each other, then the total spin will be equal to S1 plus S2 will be equal to plus 1 by 2, plus 1 by 2, which will be equal to 1. So 2S plus 1 will be equal to 2 into 1 plus 1, which is equal to 3. And this is called as the spin multiplicity, that is 3. And this is called as triplet state or the triplet excited state. Because this is the first triplet excited state, it is represented as T1. This is the first singlet excited state, therefore it is represented as S1. Since the electron can jump to any of the higher electronic states depending upon the energy of the photon absorbed, we get a series of singlet excited states. We can have S1, S2, S3, S4, S5, so on. And you can have a series of triplet excited states, T1, T2, T3, T4, T5. These are called as first triplet excited state, second triplet excited state, third triplet excited state, so on. And these S1, S2, S3 are called as first singlet excited state, second singlet excited state, third singlet excited state. It has been shown quantum mechanically that a singlet excited state has a higher energy as compared to a triplet excited state, the corresponding triplet excited state. So the energy difference is that ES1 will be greater than ET1, ES2 will be greater than ET2, and so on. So the absorption of light phenomena can take place. The electron on absorbing energy may jump from S0 to S1 to S2 or so on, depending upon the energy of the light photon absorbed. For each singlet excited state, S1, S2, S3, there is a corresponding triplet excited state, T1, T2, T3, so on. The molecule, whether in singlet excited state or in the activated molecule, returns to the ground state by dissipating its energy through either a radiative transition or a non-radiative transition. Now, the non-radiative transitions involve the return of the activated molecule from a higher excited state to the first excited state, that is S2 to S1 or T2 to T1. These transitions do not involve the emission of any radiations and are thus referred to as non-radiative or radiationless transitions. The energy of the activated molecule is dissipated in the form of heat through molecular collisions. This process is called internal conversion or IC and occurs in less than 10 to the power minus 11 seconds. The molecule may also lose energy by another process called as inter-system crossing. This process involves transition between the states of different multiplicity, for example S2 to T2, S1 to T1. These transitions are also non-radiative or radiationless. Spectroscopically, such transitions are forbidden. Therefore, they occur at relatively low rate. Now comes the radiative transitions. These transitions involve the return of the activated molecule from the singlet excited state S1 and triplet excited state T1 to the ground state S0. Such transitions are accompanied by emission of radiation. Spectroscopically, the transition from S1 to S0 is an allowed transition and occurs in 10 to the power minus 8 seconds. The emission of radiation in this transition is called as fluorescence. This is represented as a red solid arrow. So the transition from S1 to S0 is called as a fluorescence. The transition from the triplet excited state T1 to the ground state S0 is rather slow since it is a forbidden transition. The emission of radiation in this transition is called as phosphorescence. The lifetimes of phosphorescence are much longer, being of the order of 10 to the power minus 3 seconds or greater, since the transition involves spin inversion which needs time for its occurrence. Both fluorescence and phosphorescence radiations are of shorter frequencies than the exciting light. This is obviously because some part of the light energy absorbed by the molecule is dissipated in the form of heat during non-radiative transition. So just to recap, you have a molecule in the singlet ground state, it gets excited, and from the excited state it comes back to the ground state in various form. It could be done through the radiative transition or a non-radiative transition. The non-radiative transitions are internal conversion and intersystem crossing. The radiative transitions are fluorescence and phosphorescence. So the transition from S1 to S0 is fluorescence. The transition from T1 to S0 is phosphorescence. Because this is an allowed transition, it takes less time. This is a forbidden transition, so therefore it takes more time. Because both of them are occurring after the absorption, therefore they are at a longer wavelength, that is there are lesser energy as compared to the absorption of the radiation that was done. Why? Because some of the energy has been dissipated in the form of heat. Now let's just recapitulate what we have just said. The first step is the transition from the higher vibrational state within the excited singlet state to the lowest vibrational state within the excited singlet state, S1. So this is called as internal conversion. It is a non-radiative process and occurs in less than 10 to the power minus 11 seconds. Now from S1, the molecule returns to the ground state by any of the following paths. The molecule may lose the remaining energy in the form of heat, so that the complete path is non-radiative in nature. Molecule may release energy in the form of light or UV radiation, and that is called as fluorescence. This involves transition from S1 to S0. Some of the energy may be lost in the transform form S1 to T1 in the form of heat, and this is called as intersystem crossing, and this is also non-radiative in nature. After the intersystem crossing, the molecule may lose energy in the form of light in going from the excited triplet state to the singlet ground state, and this phenomena is called as phosphorescence. Now, the glow produced by methods other than the action of heat, that is the production of cold light, is called as luminescence. It is of three types. Chemiluminescence. The emission of light in a chemical reaction at ordinary temperature is called as chemiluminescence. One of the products formed is in the electronically excited state and emits radiation of the appropriate wavelength in the visible region of the spectrum. Example, oxidation of phosphorus and its trioxide in air, oxidation of Grignard reagent by oxygen. They are all exhibiting chemiluminescence. Now, bioluminescence is also an example of chemiluminescence, the glow of the firefly. This is because of the oxidation of a protein called as luciferon by the atmospheric oxygen in the catalytic presence of an enzyme called as luciferase. Now we did look at fluorescence and phosphorescence through the Jablonski diagram. Let's recall what we did. The fluorescence phenomena took place when the electron went from S1 to S0. Therefore, there was a radiation which was being emitted when the electron went from S1 to S0. So there are certain substances which, when exposed to light and other radiation, absorb the energy and then immediately start re-emitting the energy. Since these are allowed transitions that take place in very less amount of time, and such substances are called as fluorescent substances, and the phenomena is called as fluorescence. For example, organic dyes such as eosine, fluorescein, etc., vapor of sodium, mercury, iodine, they are all exhibiting fluorescence. Then the phenomena of phosphorescence was occurring because there was a transition of electron from the first triplet excited state to the singlet ground state, that is T1 to S0. Now, because this was spectroscopically forbidden transition, it was taking a longer period of time. Therefore, there are certain substances which continue to glow for a longer time even after the external light is cut off, and this phenomena is called as phosphorescence. Now, let's look at photosensitized reaction. Now, in a photosensitized reaction, what happens is you have a donor and you have an acceptor. The donor is one which can absorb light and then can transfer its energy to the acceptor. So, in the actinometer, we looked at uranyl sulfate. Uranyl sulfate was able to absorb light and was then transferring its energy to the oxalic acid. So, uranyl sulfate was the sensitizer in that. So, what happens in a photosensitized reaction is that an electronically excited molecule can transfer its energy to a second species, which can then undergo a photochemical process even though it was not itself directly excited. For example, mercury is a photosensitizer here. It absorbs light, gets excited, transfers its energy to the hydrogen molecule, which then undergoes decomposition to give you two hydrogen atoms. Similarly, in the photosynthesis, chlorophyll is a photosensitizer. Carbon dioxide and water cannot absorb light, but chlorophyll can. So, chlorophyll absorbs light, transfers its energy to carbon dioxide and water, which then undergo the process of photosynthesis to form glucose and oxygen. So, here chlorophyll is also the photosensitizer. Now, how does this happen? So, this happens through this process called as photosensitization, where you have a donor and then you have an acceptor. The donor absorbs light and gets excited to the singlet excited state, or the first singlet excited state. Now, this first singlet excited state is obviously higher in energy to the first triplet excited state. We have already talked about this. So, there is an intersystem crossing that takes place, and the electron falls from the first singlet excited state to the first triplet excited state. Now this first triplet excited state of the donor is higher in energy to the first triplet excited state of the acceptor. And because donor and acceptor are put together, so because of the collision, there is a transfer of energy from the first triplet excited state of the donor to the first triplet excited state of the acceptor. In this process, the donor loses its energy to the acceptor and goes back to the singlet ground state, whereas the triplet excited state of the acceptor happens because it has now taken the energy from the donor. And now when it has become excited, the acceptor, then it can undergo a photochemical reaction. Now let us look at this through this mechanism. There is a donor absorbs light, undergoes excitation to the singlet, or for the first singlet excited state. This first singlet excited state is higher in energy to the first triplet excited state, so there is a intersystem crossing that takes place, and it goes to the triplet excited state. This triplet excited state of the donor is higher in energy to the acceptor, and triplet excited state of the donor and the acceptor are there, and donor and acceptor are in close contact. So because of the collision, there is a transfer of energy from the donor to the acceptor. The donor goes to the ground state and the acceptor goes to the excited state. Which is the excited state? The first triplet excited state. This has become excited and therefore undergoes a photochemical process to form products, and this phenomena is called as photosensitization. In this process, the donor has gone to the ground state, so this process is also called as quenching. The reduction in energy of the donor results in quenching, and the excitation of the acceptor by the transfer of energy from the donor is called as photosensitization. It is to be noted here that the triplet excited state of the sensitizer is higher in energy than the triplet excited state of the acceptor. Otherwise, this will not take place. This phenomena was discovered by Frank and Cario in 1922. So with this, we end today's class. Let's summarize what we have done today. We looked at the various methods for the determination of number of photons, thermopile and chemical actinometer. Then we looked at the phenomena of luminescence, fluorescence, phosphorescence, chemiluminescence through the help of Jablonski diagram. We also studied about photosensitization today. So with this, we wind up today's class. Stay home, stay safe, stay healthy. Thank you.